All right, let's jump right in. Today, we're talking about one of the coolest tools in all of neuroscience. It's a technology that literally gives us a GPS for navigating the most complex, most fascinating universe we know of.
I mean, that's a pretty big question, right? You probably picture star charts, telescopes, deep space exploration. But the universe we're going to be mapping today, well, it's a lot closer to home.
Yep, we're talking about the human brain. Hundreds of billions of neurons, trillions upon trillions of connections, it's an absolute jungle in there. And for the longest time, figuring out how it was all wired together has been one of the biggest challenges in science. But now, we're finally starting to draw the map. So here's our plan. First, we'll unpack this whole idea of a GPS for the brain. Then we'll get into the, honestly, pretty genius physics of how it all works by mapping water. After that, we'll see how those beautiful brain highway maps get built, how they're making surgery way safer, and how they let doctors see injuries that used to be totally invisible. And finally, we'll take a peek at what's coming next.
Okay, so put yourself in the shoes of a neurosurgeon for a second. You have to remove a brain tumor. The problem is, just a few millimeters to the left or right are these critical pathways. You know, the ones that control a person's ability to move, or speak, or even see. If you cut the wrong wire, the consequences could be devastating. That's exactly the problem DTI was built to solve. You see, with a normal MRI or a CT scan, you get a pretty good picture of the brain's big structures. Think of it like seeing the continents on a world map. But what you can't see are the roads, the flight paths, the shipping lanes connecting everything. That's what DTI, or Diffusion Tensor imaging, gives us. It doesn't just show us the continents, it reveals the superhighways, the actual white matter tracks that carry all the information. So, you're probably thinking, okay, how on earth can a machine see these microscopic little wires inside someone's head? And the answer, believe it or not, comes down to something incredibly simple: water. The entire secret sauce here is a physics principle called anisotropy, and it's actually super intuitive. Imagine you have a handful of drinking straws. If you pour water over them, it's going to flow really easily along the length of the straws, right? But it's not going to flow sideways through the plastic walls. Well, our nerve fibers, our axons, are basically like microscopic straws. Water molecules can move up and down them really easily, but they have a tough time moving sideways. DTI is designed to spot that exact directional movement. So here's the quick and dirty on how it works. Step 1. The MRI scanner uses magnets to basically give every tiny little 3D pixel, called a voxel, its own unique address in the brain. Step 2. It sends in these special magnetic pulses from all sorts of different directions, sometimes 30 or more. And then for step 3, it just watches. It measures how far the water molecules in each little voxel move for each pulse. The direction where the water moved the farthest, boom, that's the direction of the highway in that tiny spot.
Okay, so we've got millions of tiny little boxes, and in each one we know which way the water is flowing. But how do you get from that raw data to one of those incredible, colorful 3D maps of the brain's wiring? Let's build a highway.
The first thing we do is give each of those little voxels a health score. It's called fractional anisotropy, or FA, and it's just a number between 0 and 1. A score of 0 means total chaos. The water is just sloshing around randomly in every direction, like you'd see in spinal fluid. But a score close to 1? That means you've got a pristine superhighway. All the water is flowing in one highly organized direction, which tells us we're looking at a healthy, intact nerve bundle.
And then comes the magic, a process called tractography, which is really just the world's most sophisticated connect-the-dots game. Powerful software looks at the direction and the health score of millions of these neighboring voxels, and it just starts connecting them, one after another, computationally stringing them all together until it has built a complete 3D model of an entire nerve pathway. It's amazing. Now we get to the part that really matters, the real-world impact. Because this isn't just about making pretty pictures. DTI is a tool that is fundamentally changing how brain surgery is done. It's saving lives and preserving quality of life. Think back to our surgeon. Before they even step into the operating room, DTI can create a custom-tailored map of that patient's brain. If a tumor is near the part that controls movement, they'll map the pyramidal tract to avoid causing paralysis. If it's near the language centers, they'll map the arcuate fasciculus to protect the patient's ability to speak. If it's in the temporal lobe, they'll map the optic radiation to protect their vision. It basically draws a big, bright, do-not-cross line for the surgeon, which has made these high-stakes operations dramatically safer. And hey, you don't have to take my word for it. As the research says, the potential to have a detailed view of critical white matter pathways has greatly increased the safety of many surgeries. I mean, it's pretty clear. This technology is a total game changer in the OR.
But DTI's impact doesn't stop at the operating room door. Its next massive contribution is in finding injuries that for a very long time have been completely invisible to doctors.
This has been a huge source of frustration in medicine. A patient suffers a concussion or a traumatic brain injury, they have severe, life-altering symptoms, but their MRI and CT scans come back totally normal. It's incredibly difficult for patients and doctors alike. DTI changes the game because it can actually see the microscopic damage, the tearing and shearing of those white matter highways that all the other scans miss.
And what's so powerful about this is that for the first time we can draw a direct line from what the patient is feeling to what's physically damaged in their brain. So if someone is having trouble with emotional control after an accident, we can look for damage to a specific tract called the uncinate fasciculus. Problems with memory? We can check the fornix pathway. This gives real, objective, physical evidence for injuries that used to be dismissed as just subjective.
And there's more. It can find what's called an occult stroke, a tiny stroke that other scans miss, by literally finding a dropout or a break in one of those nerve highways. And by taking scans over time, doctors can track those FA health scores to help predict which patients might have a harder recovery or are at risk for chronic problems, which means they can get help sooner.
Now, as incredible as all this is, the story is far from over. DTI is still evolving, and scientists are finding brand new ways to use it all the time.
And it's not just for the brain anymore. Researchers are using the exact same principles to map the superhighways of the spinal cord to better understand injuries and track recovery. They're even using it to look at peripheral nerves all over the body to find the exact spot of damage causing something like carpal tunnel syndrome, for example. So all of this leaves us with one last really big question to chew on. This technology gives us the map of our own internal information superhighways. And everything that makes you, your thoughts, your memories, your personality, your emotions, it all travels on these pathways. So as the map gets better and more detailed, when it's finally complete, what are we going to learn about what it means to be human? It's a pretty exciting time to be an explorer.